Hello everyone. In this lesson, we are going to start a discussion on stochastic convergence. In probability and statistics, we are often interested in the behavior of functions of sample data. That kind of functions are usually called statistics. For example, we are interested in sample mean, sample proportion, and various other types of functions of uh, sampled data, right? So, in making inferences, we are usually interested in the behavior of the distribution of such random quantities when the sample size is large. So, we want to look at how the distribution of such quantities change, how the probability is concerned related to those random quantities change as the sample size is increased. So, therefore, it is useful for us to learn uh, different behaviors of such random quantities as the sample size increases. We usually look at different types of behaviors, different types of closeness between the random variables and what it is converging to, and so on. So, therefore, different types of modes of stochastic convergence or convergence of a sequence of random variables help us understand how such random quantities behave as the sample size increases. Now, this closeness is can be looked at in different ways, different perspectives. So each mode of convergence measures the closeness in a different sense and is useful in different situations. So therefore, in this lesson, which will contain several parts, we are going to look at different modes of convergence of sequences of random variables. So we will look at everywhere convergence, almost sure convergence, convergence in probability, convergence in distribution, and convergence in uh, LP mode or convergence in mean. So those are the different modes of convergence we will be looking at, starting with everywhere convergence. So what do we mean by everywhere convergence? In order to talk about this kind of convergence, we have to consider a sequence of random variables, say for example y1, y2, y3, yn, where each y1 can be one random variable, usually based on only one observation. Y2 may be another random variable based on two observations, x1 and x2. Y3 may be some function of x1, x2, x3, like that. So like we can consider a sequence of functions. Here I denote them by y, and in some places they are denoted by x also. Those y1, y2, y3, and so on can be independent quantities. For example, if you are considering a random sample x1 up to xn, that will be independent. Otherwise, if each y uh, I is a function of several x's, then probably y's can be dependent, right? So, but anyway, we are looking at a sequence of random quantities, y1, y2, y3, and so on. And we want to look at what whether this sequence of random quantities converge to some random variable or a constant, whether the distribution of those quantities converge to some distribution, whether the probability concerning these random variables are converging to some value, and so on. Right? So we look at the definition for the everywhere convergence. Now, a sequence of random variables yn is said to converge everywhere, or sometimes called pointwise everywhere, to a random variable y if for all omegas, that means all the outcomes in capital omega, that is the sample space, limit of yn omega as n goes to infinity equals y of omega. Remember, these are random variables, so they are evaluated at the uh, outcomes in the sample space, right? Random variables are functions from the sample space into the real line. So if yn is a random variable, we can evaluate yn at some outcome omega, right? So we say that sequence yn converges everywhere if uh, yn omega as n goes to infinity is equal to y omega for each omega in the sample space. Right? That is, the convergence holds for every sample point, simple omega in capital omega. We can tell the same thing mathematically like this. Suppose, for example, uh, you consider an omega value, simple omega, that is an outcome in the sample space, and you calculate yn omega, yn omega. And if yn omega as n goes to infinity is the same as y omega for some other random variable y defined on the same sample space. So then we put that omega into set A. Let's take another omega and then look at the limit of yn omega as n goes to infinity. Check whether that is equal to y evaluated at omega. If that is the case, put that omega into set A. So like that, consider set of all omegas satisfying this condition, right? Each omega is put into A, right? So once you do that, if A finally is equal to the whole sample space, then that means for each omega in the sample space, this condition is satisfied. So that means yn omega as n goes to infinity equals y omega for each omega in the sample space. So therefore, A will become the sample space. If such a set of omegas satisfying this condition is equal to the sample space, then we say that yn converges to y everywhere. Right? So that is actually a very, very strong mode of convergence. Very strong mode of convergence. And usually we don't consider this as a very practical type of convergence because it's very rarely this type of convergence occurs. But we can understand this again. To understand what this really means, let's consider several steps, right? So as I have already mentioned, let's consider a fixed simple omega in capital omega. Capital omega is the sample space. Simple omega is an outcome. For this fixed simple omega, consider the sequence of real numbers. Say y1 is some function of data. So y1 evaluated at omega is a real number. Y2 is another function of omega, another function of the random variables. Uh, if when you evaluate it at omega, you get a real number, right? So like that, consider the sequence of these real numbers for a fixed omega. And also find out the value of y omega for some random variable that is mentioned or assumed y omega, right? So check now whether this sequence of y1 omega, y2 omega up to yn omega converges to y omega as n goes to infinity, right? If that is so, then put that omega into set A, include that in A. Take another omega, simple omega, and check, consider this corresponding sequence, y1 omega for that omega, y2 omega for that omega, y3 omega for that omega, and y omega for that omega. And if the new yn omega value sequence converges to y omega, then put that omega into set A. So do that again and again and again for all omegas in the sample space. Then if A finally equals the sample space, then we say that yn converges to y everywhere, right? So that is how we can understand what this convergence means. Everywhere convergence is usually too strong for most statistical applications because it's very rarely this type of convergence occurs. That means if you look at all the sample points, that means the elements in the sample space for which yn omega is equal to y omega as n goes to infinity uh, is equal to the sample space happens very rare, right? So in statistics, we often work with random sampling and probabilistic behavior. So allowing convergence to fail on a probability zero set is generally acceptable, right? So that what that means is even though the previous condition doesn't uh, happen for all omegas in capital omega sample space, there might be few at uh, sample point or outcomes of simple omegas for which this condition is not satisfied. As long as the probability of that set for which the condition is not satisfied is equal to zero, we don't worry, right? So therefore, requiring this condition to be satisfied for each and every omega in the sample space is too strict, right? It is enough for us for this kind of condition to satisfy for a set of omega values for which probability of A will be equal to 1, so that there might be some other point, say B, where this condition doesn't happen, but the probability of that set is 0, right? So therefore, we usually look at that kind of requirements rather than convergence everywhere, right? So the modes of convergences that allow that kind of convergence are almost sure convergence, convergence in probability, convergence in distribution, and convergence in mean. So therefore, in practice, usually we consider those type of or those modes of convergence. Convergence almost surely, convergence in probability, convergence in distribution, and convergence in LP mode. So now we will look at those types of convergence. But before that, I will just give you one example where the convergence everywhere will happen. But this is just a created example, not a very practically useful example, but just to show you there are situations where this kind of things can happen. So let us consider some sample space, a corresponding probability measure and uh, sigma algebra F with the probability space. And here let us consider that sample space is a subset of the real line. Let us assume that our sample space is a subset of a real line. And define a sequence of random variables yn like this. Yn evaluated at omega will be equal to omega plus 1 over n, right? Because now capital omega is a subset of R. This simple omega will be a real number, right? So therefore, omega plus 1 over n is meaningful, right? So let us define y in omega to be given by this value. So then we can talk about y1 omega, y2 omega, y3 omega, y4 omega, and so on. So in general, we can talk about y1, y2, y3, y4, and so on. Sequence. And let us define another random variable y on the same sample space as y omega is equal to omega. Right. Now we can easily see for a fixed omega, uh, y and omega as n goes to infinity is equal to omega because this 1 over n goes to 0 as n goes to infinity. So therefore, as n goes to infinity, y and omega becomes omega, which is equal to y omega. So therefore, for any omega in the sample space, this condition is satisfied. And that is satisfied for each omega in the sample space, right? So if you consider the set A, which satisfies this particular condition, and A will be equal to the capital omega, the sample space. And therefore, according to the definition of convergence everywhere, this sequence yn converges to y everywhere. So there is just a mathematical example to show you what we mean by convergence everywhere. Right. As I mentioned, but convergence everywhere is not very practical. Therefore, we usually look at other types of convergences. Out of those, the strongest practical type of convergence is almost sure convergence. Very strong, only very little weaker than everywhere convergence. It allows the sequence to fail to converge at some points, but only at a set of outcomes that has probability 0, right? So in the previous one, we don't have that kind of set where the convergence doesn't happen. But as I mentioned previously, it's enough for us to consider a situation where there might be some outcomes. Uh, for those outcomes, the sequence y1, y2, y3 may not converge to y or may not converge at all. But if that set of values containing that kind of omegas have probability 0, then we don't worry too much. So therefore, we consider that kind of convergence, right? So that convergence is called the almost sure convergence. Almost sure convergence because the set of simple omegas on which the sequence of random variables converge to, say, y or x, whatever, has probability 1, because the bad set on which the convergence doesn't occur has probability 0, right? So mathematically, this is how we define the almost sure convergence. A sequence of random variables xn, previously I mentioned yn, but now actually it's denoted as xn. It's okay, you can use yn if you want. A sequence of random variables xn is said to converge almost surely to random variable x if this condition is satisfied, or in short, if this condition is satisfied. So what is this condition? We are looking at the probability of some event being equal to 1. What event? Let's consider xn omega minus x omega, right, equal to 0, right? So find out all the omegas in the sample space capital Omega, so that xn omega minus x omega as n goes to infinity equal to 0, right? So for example, there is some omega 1. When you put, when you consider xn omega 1 minus x omega 1 as n goes to infinity becomes 0, if the difference between xn omega 1 is a real number, x omega will be a real number. So the difference between those two will be a function of n. As n goes to infinity, if that goes to 0, then that condition is satisfied. So then omega 1 will be in a particular set. Suppose we consider another omega, omega 2. For that also, say xn omega 2 minus x omega 2 as n goes to infinity becomes 0, then x2 will also be in that particular set. Let us say that is A, right? And when you consider all the set of all omegas that satisfy this particular condition is, say, for example, capital A, and if the probability of that A is equal to 1, then we say that uh, xn converges to x almost surely. So almost sure converges. But notice that when you say that the probability of that set is equal to 1, it doesn't mean that the set A, capital A that I consider, is not necessarily equal to the sample space. There might be some points in the sample space which are not included in our capital A, but the probability of that set has to be 0, right? So there can be situations like that, right? So there is a set A on which this condition, xn omega minus x omega is equal to 0 as n goes to infinity, and the probability of that set is equal to 1. But there might be another set of values where this condition is not satisfied, but the probability of that set has to be 0, right? So if that happens, then we say that xn is converging to xn almost surely. Right. So to understand this again, I put that in several steps just to go one by one. So let us fix some omega value like omega 1 as I mentioned earlier. Fix sample point. Sample point means here is an outcome in the sample space, right? For this fixed omega, consider the sequence of real numbers x1 omega, x2 omega, x3 omega, and so on, and also the value x omega. The same thing that we did for everywhere convergence. Check whether this condition is satisfied. So whether the difference between x and omega and x omega, so this is a real number, this is a real number. So this is the difference between but this will be generally depending on n. So see whether this difference goes to 0 as n goes to infinity. Right? If that happens, put that omega into some set, say capital A. Right? So repeat this for each omega in the sample space capital omega. So collect all sample points omega for which the above limits hold and define A to be the set of all omega satisfying that condition. So this is the set of sample points or the outcomes where the convergence is successful. Successful. But as I mentioned, there can be another set where a set of omega values where this limit either is not equal to x omega or the limit doesn't exist. Right? So that is a kind of a bad set of sample points or outcomes where the convergence fails. So for almost sure convergence, the bad set need not to be empty. It may be non-empty. There may be some outcomes in that set, but the probability of that set has to be equal to zero, right? Remember, a set here generally an event, so that we can talk about probability. So the probability of that bad set has to be zero, and equivalently, probability of the good set where the convergence occur, set of omegas uh, for which the convergence occurs, the probability has to be equal to 1. If that is the case, then we say xn converges to x almost surely. So that's how we write down on the arrow, we write down a dot s dot to denote almost sure. The almost sure convergence or convergence with probability 1. Right. So that is the strongest practical mode of convergence. So let us look at one or two examples to understand this type of convergence. Suppose we collect an infinite sequence of independent measurements or observations from a population with uh, true mean mu, and there may be some variance, but we are interested in only the mean. Usually this mean is an unknown thing, but theoretically, there's suppose the mean is mu. Then we can show that the sample mean x n bar will converge almost surely to mu. Right. So here in the definition we define the convergence of the sequence of xn to random variable x, but in the same way we can talk about convergence of a sequence of random variables to a constant also. Right. Okay. So here, suppose that an outcome is omega, where omega is a infinite sequence of observations or possible observations, x1, x2, x3, and so on. If we take observations from a certain population, this population of interest, right? So this is actually not a really observed set, but it's possible set of infinite observations. So that is one, right? So these x's can be rearranged or they may be completely different. So depending on that, you will have omega 1, omega 2, omega 3, large number of different possible outcomes. Now let us define xn to be the nth element of a given omega, nth element of a given omega. So xn evaluated for that particular omega, let us define it as the nth element in this omega. Xn omega is equal to simple xn, which is the nth component of the sequence of sequence omega. And also let us define xn bar omega to be, so that is another random variable, xn bar omega to be the average of the first n elements in omega, right? So here xn bar is the function, we are evaluating it at omega. So let us define xn bar omega to be the average or the sample mean of the first n elements in omega, right? So xn bar is the mean of the first n components of the outcome sequence omega. Now, there is a law called strong law of large numbers. That means actually that is actually telling you that xn bar, so you can consider a sequence x1 bar will be just the x simple x1, x2 bar will be x1 plus x2 divided by 2, right? For a particular omega, for that omega, the mean of the two observations, x3 bar will be for that particular omega, the first three components of the mean of the first three components and so on. So for that omega, we can show that xn omega, xn bar omega converges to mu almost surely. So that is called the strong law of large numbers. So here, I'm not going to prove it. This is one application. That's a very useful and very strong type of theorem. Strong law of large numbers. So generally what it means is the sample mean converges to the population mean almost surely. Right? So if you consider all the sequence of observations, infinite observations, right? Then there might be one or two sequences where this doesn't happen, right? Few sequences where this doesn't happen, right? But if you consider the set of omegas where this happens, then the probability of that set will be equal to 1. So therefore, we can say that xn bar omega converges to mu almost surely, right? So mathematically, what it means is that set, if you consider the probability of the set of omegas, where the limit, uh, the difference between xn bar omega minus mu as n goes to infinity becomes 0 is equal to 1. So, however, there might be some sample points omega in capital Omega for which xn bar omega either does not converge to the population mean or may not converge. It might be even be divergent as n goes to infinity, but the probability of that set is equal to 0, right? Especially when the random variables considering are continuous, right? This is very easy to see happening this kind of thing, right? Very, very rarely. So there will be millions or billions of possibilities. Out of that, there may be one or two situations where this sequence, right? So for a given, there may be one or two omegas where each omega is a sequence of infinite components. There may be few omegas out of millions or billions of possible omegas where xn omega, xn bar omega doesn't converge to mu. But for all the others where the probability is equal to 0, that converges occurs. Therefore, we can say xn bar converges to the population mean mu almost surely. That is one very useful result, right? Another result is regarding the uh, convergence of a sample proportion to the population proportion. So actually, this is a particular case of the previous situation. In the previous situation, we were considering generally simple x1, simple x2, simple x3, and so on. So those can be any number. But if you, for example, now consider the same thing, repeating uh, some experiment again and again and again. Suppose x1 is the outcome in the first experiment, x2 is the outcome in the second experiment, and so on. Suppose you are in particular considering Bernoulli experiments, where the outcome can be classified as success or failure, and x value, simple x value, will be taken as 1 or 0, it will be 1 if the outcome is a success, otherwise it will be a 0, right? So your each of x1, x2, x3, and so on will be either 0 or 1. So when you take a omega, it will be a sequence of zeros and ones. Particular omega, simple omega, will be sequence of zeros and ones, right? So if you consider, for example, the mean of the first uh, n components in that sequence, that will be uh, the number of ones divided by n. And that is actually going to be the sample proportion of successes in the first n experiments. So let us denote it by Pn omega, right? For a particular omega, Pn omega is the uh, sample mean of the first n components in omega. So that is actually practical interpretation is the sample proportion of successes in the proportion of success in n Bernoulli experiments. Right? For example, if you are considering this Bernoulli experiment to be, say, tossing a fair coin, then in that case, this Pn omega for a given omega will be converging to zero point 0.5. Right? In the previous example, xn bar was converging to the population mean mu. Now, if you are considering tossing a coin, for example, it will be, in that case, the expected value of your random variable x is equal to uh, P, right? For a Bernoulli random variable, expected value is equal to P, where P is the probability of a success. So if you are tossing a fair coin, it will be zero point 0.5. So therefore, uh, in this case also, we can show that this Pn, sequence of Pn converges to zero point 0.5, almost surely, right? So that is again a particular uh, uh, case of strong law of large numbers, right? Where the x, simple x1, x2, x3, and so on are zeros and ones, right? So for almost every sample path omega, then if you consider a particular set of omegas where this particular condition happens, right? P n omega minus zero point 0.5 as n goes to 0 is equal to, as n goes to infinity is equal to 0, right? So you are considering for a fixed omega, P1 omega minus zero point 0.5, P2 omega minus zero point 0.5, P3 omega minus zero point 0.5, and so on, a sequence of real numbers. So if this sequence of real numbers converges to 0, that omega is considered into our set, say capital A. So if you look at this thing for all possible simple omegas in capital omega, a large number of simple omegas in capital omega will be coming into our set capital A, and the probability of that capital A will be equal to 1. There might be few uh, omegas where this condition doesn't happen. Oh, that means P and omega is not converging to zero point 0.5. It may be converging to some other value, or doesn't converge at all. But the probability of that set will be 0, right? So therefore, according to the definition of the almost sure convergence, the sequence Pn will converge to zero point 0.5 almost surely. Right. So that is the most practical, strongest mode of convergence we usually talk about. Right. Uh, Next, we are going to consider a different mode called convergence in probability. Convergence in probability. Okay, so instead of requiring the variable to get close for all paths, convergence in probability requires that the likelihood of them being far apart shrinks to zero, right? In the previous one, we were considering the difference between xn and x. So we are looking at the difference between the two random variables, and uh, what we are looking at is they are becoming close, and the sequence of xn is becoming close and close to x as n goes to infinity. But in the convergence in probability, we are looking at a different kind of thing. We are going to look at the difference set of values omegas, uh, where again here the notation has changed. Instead of xn, I'm using yn again, yn, and suppose there is another random variable y. So first let us look at the definition, and then we can discuss the meaning of it. So sequence yn converges to some random variable y in probability if for any tiny positive number omega, the probability that the distance between yn and y is greater than omega goes to zero as n increases. Right. So here we are looking at the probability, limit of probability. In the previous one, we were looking at probability of a limit, right? If we go back and look at the definition here, you can see that we are looking at a probability of a set where a certain limit occurs, a condition with a limit occurs. But here we are looking at the limit of a certain probability. The probability of what? For if you consider a very small omega value, positive value, let's consider the probability that yn minus y greater than or equal to omega. And if that probability we can consider, for example, y1 minus y, a probability that y1 minus y greater than or equal to that fixed omega. So let's call that P1. We can consider probability y2 minus y greater than or equal to omega. Let's call that y2. Sorry, P2. Like that, we can calculate P1, P2, P3, and so on with different n, right? P1 will be the probability that the absolute difference between y1 and y becoming greater than or equal to omega. Remember, in this case, we are considering this yn and y are all defined on the same sample space, right? So we can consider a sequence of each P1 will be a real number between 0 and 1. P2 is a real number between 0 and 1. All are probabilities, but there is a sequence of probabilities now. So if this sequence of probabilities goes to 0 as n goes to infinity, for any omega, then we say that yn converges to y in probability. Yn converges to y in probability. So, okay, that is the definition. So if we define the sequence of real numbers, say, for example, as I mentioned, omega is a selected value. So usually we select a very small value. There's no point of selecting a large value. What we want is the probability, the difference between the sequence yn and y to be as close, as small as possible. Them to be as close as possible. So therefore, we are considering the probability that the difference between these two, absolute difference, because yn can be above or below y now. So therefore, we are considering the geometric difference. So that's why we are considering absolute value. So the difference, the length between y and omega and y omega being greater than or equal to a very small number. That's what we are considering, the probability of that. Let us define that as P n omega. Right? So that means for a given omega, P1 omega is the probability that y1 minus y absolute value greater than or equal to that omega. P2 omega is the probability that absolute y2 minus y greater than or equal to omega. So as I mentioned, there is a sequence of P1 omega, P2 omega, P3 omega, P4 omega, and so on. Each is a real number. So we can see whether for that particular omega, uh, whether P and omega converges to zero as n goes to infinity. And if that happens for each omega, then we say that uh, the sequence yn converges to y in probability, right? So what you are looking at here is actually when you consider the probability p and omega, so that's going to be the probability of some set, no, some event. So we can explain it like this also. Let us consider, let's say A1 is the set of omegas. That is, omegas means set of simple omegas, outcomes in the sample space. Right. So let's say A1 is the set of outcomes in the sample space, so that y1 omega minus y omega is greater than or equal to epsilon. A2 is the set of simple omegas in capital omega, such that y2 omega minus y omega absolute value greater than or equal to this selected epsilon, and so on. So let us consider these sets. So they are events. So we can talk about the probability of those. Say, let's say P1 is the probability of this set, probability of this set is P2, and so on. So you have a sequence of real numbers, right? Now let us consider the limit of this sequence of real numbers. If that limit goes to zero, then we say that the sequence yn converges to y in probability. So those are the very common type of convergence that we are interested in practically most of the situations, right? So just to again recap the difference between these two, as I mentioned in the almost sure convergence, we are looking at the probability of some set of omegas where a certain condition on a certain limit occurs. Limit is inside the probability. Condition with limit is inside the probability. In probability, a limit is in the outside. We are calculating some probability, sequence of probabilities first, and then look at whether that sequence converges to zero. Here we are looking at a sequence of we are finding a set of omegas where this sequence is converging to y omega as n goes to infinity, right? So consider each possible omega and look at uh, for that fixed omega, yn omega minus y omega, whether that is the difference is converging to zero as n goes to infinity. If that is the case, put that into a particular set, say capital A, and then if the probability of that set A is equal to 1, then we say the sequence yn converges to y almost surely. Right. So just to consider an example of convergence in probability, there's a theorem called the weak law of large numbers. Remember, as an example of almost sure convergence, we talked about a strong law of large numbers. This one is called weak law of large numbers, right? So weak law of large numbers says that it guarantees that a large amount for a large enough sample, the sample average will be very close to the true population mean with high probability. So again, the same idea, but now here notice again, earlier in the previous large strong law of large numbers, we talked about converging xn bar, the sample mean, to population mean almost surely, right? Converging xn bar to mu almost surely. Now we are talking about converging again xn bar to mu in probability, right? That also happens. Of course, if one sequence converges to some random variable or constant almost surely, that implies that it converges in probability too, right? So, but if you are considering the convergence in probability, in that case, converging xn bar to mu in probability is called the weak law of large numbers. Right? So we can prove that also. So mathematically, what we are meaning here is the probability that xn bar minus mu absolute value greater than or equal to epsilon for any small epsilon becomes zero as n goes to infinity. So here, as I mentioned, we are looking at uh, a sequence for a fixed epsilon. We are looking at a sequence of probabilities and with checking whether that sequence of probability converges to zero, right? And that will happen especially for the sample mean, right? If your random variable that you're considering is sample mean with sample size n, xn bar, and that will be converged to the population mean in probability. So that is what we call the weak law of large numbers. Here I have actually done some simulations to show you this idea of weak law of large numbers. What I did was I generated some uh, samples from a normal distribution with mean 50 and variance 25 for different n values, say n equal to 2, n equal to 3, n equal to 4, up to n equal to even 1000, right? So what I did was for a fixed n, I calculated xn bar and then I know the mean is equal to 50. So I did this again and again and again 10,000 times for that fixed sample size n. So for example, take a sample of size 5, calculate x5 bar, look at the difference between x5 bar minus 50 absolute value. I have taken, I think, epsilon to be zero point 0.5 here. So I looked at out of 10,000 times, how many times the difference between x5 bar minus and 50 was greater than zero point 0.5. So when I divide that number by 10,000, I get an estimate of the probability that x5 bar minus 50 is greater than epsilon. So I get the estimate of that probability. Right. I can theoretically also calculate that for the normal distribution, but what I did was I simulated and then take another sample size, say 10, for example. So generate one sample of size 10, calculate the sample mean, check whether the difference between sample mean and population mean is greater than zero point 0.5 or not. If it is greater than zero point 0.5, then I count it. Take another sample to size 10, calculate sample mean, look at the difference between sample mean and 50, check whether it's greater than zero point 0.5, like that. I did it 10,000 times for that fixed sample size. And from that, I calculate or estimate the probability that x10 bar minus 50 is greater than zero point 0.5, right? So like that, I did it for different n values for each n 10,000 simulations. And then by that, I calculate the probability. So I have P1. P1 is the probability that x1 bar minus 50 greater than zero point 0.5. P2 is the probability that x2 bar minus 0.50 greater than zero point 0.5 and so on. I calculate those p's and I have plotted those p's here. The probability Pn is on this axis. That is the probability that xn bar minus mu greater than epsilon. So you can see that that Pn is now getting smaller and smaller and smaller and converge into zero, right? As n goes to n increases, right? So here I have done up to n equal to 1000, right? So this is what we mean by the weak law of large numbers, right? So this is the next type of convergence is the convergence in distribution. And there is another type of convergence, convergence we call LP convergence, or convergence in peak power of the mean. Um, I will discuss about those two types of convergence in the next lesson, because for this lesson, I think time is almost over. So therefore, in the next lesson, we will talk about convergence in distribution, convergence in mean. Convergence in distribution is a completely different type of convergence than the previous types of convergence. And also convergence in the mean is also important. And then finally, we will we will see that some types of convergence imply the other type of convergence. If, for example, if uh, there's a convergence almost surely, that implies that there is convergence in probability, but not the other way around, right? So we will discuss those things in the next lesson.